Hello everyone, my name is Sukhjit Singh and I'm studying in SGDB Khalsa College, Delhi University. So today I'll be telling you guys about the Michelson interferometer. So from starting, the Michelson interferometer is basically a very common type of configuration used for optical interferometry. So what we do here is that using a beam splitter here, we split the light source into two arms. Now each of these light beams is reflected back towards the beam splitter, which then combines their amplitudes using the superposition principle. So also the resulting interference pattern that is not directed back towards the source is typically directed to some type of photoelectric detector or some other type of camera. So let's begin. So today we'll be discussing about these four topics mainly. We have application and interesting facts. Then we have important basic terms. We have then figures and theory. And then we have these formations and shapes of fringes. So let us begin. So we have here first applications. So the first application is to determine the wavelength of a monochromatic coherent sources like sodium lamp. So we all know that the Michelson interferometer, like we stated in its definition, it can be used to determine the wavelength of some monochromatic coherent sources. Now we have here like sodium lamp. So monochromatic here means the a light beam which whose wavelength remains constant. And up to coherent we will get back here. So let's go for application 2. Okay, so the most basic use that we have for Michelson interferometer is to determine the wavelength difference between two different light sources. Now here we can see a setup of how the light waves are transmitted and we see their fringes and everything. We'll get back here in some minutes. And okay, so let's see this application 3. So stellar measurements. So the Michelson stellar interferometer is used for measuring the diameter of celestial bodies like stars. So you all will be thinking about it like how a simple setup like this can be used to measure the diameter of celestial bodies like stars. So we all have heard about radio astronomy. So in basically what we do here is that we have here, let's see. Okay, so in radio astronomy, let's imagine a wide open field. So there we plant various radio telescopes, small, which can measure radio frequencies from about 20 hertz to 350 hertz. So like the upcoming SK project, Square Kilometer Array. So what we will do here is that we will gather the light sources from, let's see that here is a star here, and there are a lot of radio telescopes here scattered over a large field. So the radio waves will come and all will be one part of the radio telescope will measure some receiver will receive some, and all of those radio waves they will be combined using a mathematical technique. So they will all be superimposed into a single wave which can be then used to create high definition resolution images. And also we have this fourth application, gravitational wave detection. So the Michelson is the leading method of interferometry for the direct detections of gravitational waves. So we have here, for example, LIGO, and as you can see, this is the LIGO detector and this is the Virgo detector. So the upcoming projects like LIGO India, and there's also Kagra detector in Japan, they all use this basically the same thing where they use the setup of these light waves, and the gravitational waves, what they do is that they create small minuscule changes at the scale of photons in the space-time sheet. So when those changes occur, the light beams being recorded, they are changed by a very minuscule amount in the Michelson interferometry setup. So using advanced detectors and using advanced sensors, we can measure those tiny minuscule changes. And those tiny minuscule changes is what gives the detect the proof of gravitational wave detection. Okay, so interesting facts. So fact number one is Albert A. Michelson. So in 1907, Albert A. Michelson received the Nobel Prize in Physics, becoming the first ever American to be awarded the Nobel Award in Science. So basically, what he did is that using this Michelson interferometry setup, he measured the uh, he had the first standard meter proof in terms of the wavelength of any light source. Okay, so fact number two. So the Nobel Prize in Physics in the year 2017 was awarded to three physicists for their decisive contributions towards the LIGO, the Laser Interferometry Gravitational Wave Astronomy Detector, and their observation of gravitational waves. So what happened was that in the year 2015, these three physicists did analysis of the gravitational waves on the LIGO setup, which uses the principle of Michelson interferometry. So using this simple technique, we were able to get proof towards one of the biggest contributions of the 20th century, of this 21st century. It was a proof that the Einstein's general theory of relativity ca is right even under the most extreme of circumstances near the black holes. So we can get an idea that how a simple thing like Michelson interferometry setup can be used to prove the biggest of the hurdles of science. Okay, so let's begin. So we have here some important basic terms. So there is source and interference. Okay, sources. So there are two different types of sources. So the first source is coherent waves. So these are the type of waves that are in the same phase or their phase difference is constant. So we have, for example, laser. So basically the laser, its waves are in the same phase. Its wavelength does not vary upon upon larger distances of time. So we have here a setup. So we can see that how these waves follow a very normal pattern, a very similar pattern. These all waves are going in the same direction, a similar pattern. So when physicists see these type of things, we say that these are coherent type of waves. So the second type of waves are incoherent waves. So these are the type of waves that are not in the same phase or their phase difference is not constant. So we have, for example, bulb, lamp, sun, etc. So as you can see here, like let's see this topmost wave. This wave is following a given pattern. It is going in a given direction in a different pattern. And if we see the wave beneath it, we see that this waves follow a another different kind of pattern, and it is going on in another direction in a different pattern. And same can be said for the other types of waves. So when we see these type of patterns out there, we say that these are incoherent waves, the waves which are not in same phase with each other, or their phase difference is not constant. So interference. So interference is a phenomenon in which two waves superimpose to form a resultant wave of greater, lower, or the same amplitude. So there are two types of interferences observed among light sources. So we have here a constructive interference and destructive interference. Okay, so constructive interference. So constructive interference occurs when waves come together such that they are in phase with each other, and so the resultant wave will have a greater amplitude. So basically, so the constructive interference waves, the waves which do the process of constructive interference, they're always in phase with each other. Being in phase means that the pattern of their waves, it will be similar. So we see here there's a wave 1 here which is following a given pattern, and also when we see this wave 2, it is also following a similar pattern. So when these two light waves, they will meet with each other, when the crust of this wave meets to the trough of the other wave, they will superimpose with each other, and they will give rise to something called a process called constructive interference. So this wave will have a greater amplitude, which is equal to the sum of the previous two waves combined. So we also see a similar kind of interference, but something different. So we have here a destructive interference. Okay, so destructive interference occurs when waves come together in such that they are not in phase with each other, and so the resultant wave will have a lower amplitude. So we see here a wave. This wave is following a similar pattern as compared to the different one, as compared to the previous one which we saw in the previous slide. But when we see this wave 2, we see that it is not following the same pattern anymore. It is something different. So as a result of this, these are incoherent waves right now. So when these two waves will meet each other, when the crust of this wave meets with the trough of this wave, they will try to finish up each other. Uh, the amplitude will be lower. So we see this type of wave. The wave will know we know more, and this is what we call a destructive interference. So the wave which we will found will have a lower amplitude as compared to the both of them. Okay, so constructive interference and destructive interference. So we have discussed their definitions. So let's see the mathematical representation by which we see how these waves are, how we can determine them, which is a constructive and which is a destructive. So the path difference between them is delta is equal to 2n multiplied by lambda by 2. So we have for constructive interference and lambda, and for destructive interference there is 2n plus 1 lambda by 2. So what we see here is that when we see here n is a positive integer. So when we start putting in values here, and lambda gives values like lambda, 2 lambda, 3 lambda, 4 lambda. So we notice that the waves which are of the integral multiples of this, or we can say that which are integral values or integers. So n lambda, lambda, 2 lambda, 3 lambda, when these type of waves will superimpose with each other, we will see constructive interference. But as we start plugging in values here, let's see 2n, let's put n is equals to 0. So we have 2 times 0 plus 1 into lambda by 2. So we have lambda by 2. So let's put n is equals to 1. We will get 3 lambda by 2. So we see that lambda, 3 lambda by 2, 5 lambda by 2. So when we see here, when we have this fractional representation of these values, or we can say that the lambda, the integral multiples of lambda by 2, we notice destructive interference. So we see that these waves will superimpose with each other, and they will give rise to this type of pattern that we are seeing here. Okay, so this is the setup of a Michelson interferometer. So this here is a source. The source is where the light beams is coming, and this is what we call a beam splitter. So what the beam splitter does is that it it reflects the light ray, a part of the light ray along a different path, and sends a part and transmits a part of a light ray as per the difference in the normal direction, or we can say this fixed mirror. And we have here is the compensating plate, and when these light waves come back and interfere with each other, they are deposited here, or we see that it is called this detector, and we can see these fringes, or here we have, for example, sodium fringes. Okay, so this is the normal representation. So we have here this S source. So the light, when the light waves go, will so this source, what does it do is that it emits light waves along different paths, and so we have here is a convex lens, and what it does is that it sends the light waves along a same path. So this is our beam splitter here. It is at an angle of 45 degree with respect to the path of the light wave. So when the light waves come here, so what does the beam splitter do is that it reflects a part of light waves towards the mirror M1, and sends a part of the light waves across this M2 mirror, or the transmitted waves. Okay, so let's say that the light waves will be going through here, but the optical difference, let's see this. Uh, so after lens, we will put two glass plate P and C of the same material and same thickness. Okay, so plate P is semi-silvered, so that some of the incident ray will be reflected and some part will be transmitted. So this is semi-silvered, and some will be transmitted and some will be reflected. Okay, so we put two mirrors M1 and M2 normal to each other and at the same distance from point O for reflection. Mirror M1 is moving vertically, and both of these plates which we are seeing here, they are at an angle of 45 degree with respect to each other. Okay, so let's get down for theoretical explanation. So when a wave incident on plane P, so then the some part of the incident ray is reflected towards mirror M1 and some of it will be transmitted towards mirror 2. After reflection on both mirrors, waves transmitted back at point O and interference happened. So what we will see here is that just a sec. Okay, so when these light waves, one will be sent towards here and other will be sent towards here. Okay, so when these light waves come back, they will meet here, and then we will see the process of interference happening. Okay, the waves make fringes after interference. These fringes can be seen either by direct eyes or through telescope. Okay, so function of compensating plate. So we see here a function of it, example of it without putting in compensating plate. So in order to understand its importance, let's see. So in absence of plate C, reflected ray passes twice through plate V, while transmitted ray does not pass at all. This happens because therefore in absence of glass plate C, the optical paths of both rays in glass are not equal. So what's happening here is that the optical path length of the light wave depends on this beam splitter's index of refraction. So what happens is that after the transmitted ray passes through here, its optical path length changes, so that when the light wave when it will come back, it will not pass through this at all. So what we do is that we put a compensating plate here with the same thickness and the same optical path length to compensate for the change in the refraction, so that when the light ray will come and gets reflected back towards it, the optical path length of the light itself doesn't changes. So to make these paths equal, we put plate C of the same material and same thickness as a plate P. Okay, so we have here this. So now we will be studying about the path difference. Okay, so let's say that there is a mirror S which is giving off light. This is a L. This L is a mirror, and this here we have P, which is beam splitter, and then this is the change in wavelength. Okay, so from an observer point of view, he will see the M1 mirror first, and a virtual image of M2, which is the as perceived by the observer, he will see that later. So so both of these mirrors, they will generate uh, two two images that are S1 and S2. Okay, these will be the images as seen from the mirror M1 and M2. This here is the distance 2D traveled by the light wave, and this is the mirror M1, and the change in lambda will be given by this formula 2D cos theta. This angle theta here, it is the difference between the mirror M1 and M2. Okay, so see, so for bright fringes and for dark fringes, so we have seen right now that we observe fringes the on the detector. So we will be seeing there two types of fringes, bright fringes and dark fringes. So bright fringes happen when there will be a constructive interference. When constructive interference happens between those two waves, we will see a bright fringes. And for dark fringes, we will see that there will be a destructive interference. So when destructive interference happens, we will see those dark fringes. Okay, formation and shape of fringes. So the formation and shape of fringes will depend mostly on these, most importantly of these things. So we have here a D, distance between the mirror M1 and M2 dash. So what is the distance between them? So let's say that when we saw here that hmm, okay, so due to the changes of this, let's say that the light ray travels through here and it comes back. So the light ray will be traveling a distance of this 2D. So more the distance, more the lesser the distance the light ray will actually have to travel, and the changes in those distances, how those distances change linearly with each other, it will determine that what kind of fringes we will observe actually. Okay, so theta. So we have seen that the inclination between mirror M1 and M2 dash. So one of the mirrors there will be the mirror M2 will be fixed, and the mirror M1 can move freely. So that how it will move, the type of the whether it is forward, uh, it's inclined towards the other end. It will change the angle between both of those mirrors, and it will determine the kind of shapes and fringes we will may observe. So the air film between mirror M1 and M2. So the kind of medium. So let's say that the air is normal, or there's some other type of gas present there, or let's say there are a lot of particles present in the medium the light ray is traveling. So it may affect the how which kind of fringes we may observe, because the light ray will get reflected from them. Okay, so we will get three different types for different conditions. So we have circular fringes, hyperbolic fringes, and linear fringes. Okay, so circular fringes. So if theta is equals to 0, then we will get circular fringes. Number of fringes will depend on the value of d, as we just discussed. So we will get this circular fringe to be dark for d is equals to 0. So suppose that the distance between both of them is 0, then we will observe these type of circular central fringe. So if we increase the value of d, then number of fringes will also increase, and radius of fringes will decrease. So the formula, as we saw, it is lambda is equals to 2d cos theta. So let's say if we increase the value of d, so we have a large value of d within a small space. So to compensate for it, the radius of fringe will decrease, so that the angle remains same, but the number of fringes will, as seen at a particular place, they will increase. Okay, so these type of fringes that we observe here, the circular fringes, they are also called Haidinger fringes. Haidinger fringes. So this is here a presentation that we may see of the fringes after the experiment. For d is equals to 0, this is the kind of central fringe we were talking about. we may observe this kind of fringe to be there. For lambda by 4, we see this, and similarly for lambda by 2, we may observe these type of fringes on the screen, and for d is equals to lambda, we may observe these type of fringes. Okay, so now you're talking about the hyperbolic fringes. So if theta is not equal to 0 and both mirrors are separable from each other, that is, they are not crossing each other, then we will get hyperbolic fringes. These fringes are also called localized fringes. So we will get a hyperbolic curve here at like a broader angle. Let's see. So we will get the following representation of fringes after the experiment. So here's we have both the mirrors, mirror M1 and mirror M2, and after the experiment, we will see these type of fringes. So as you can see that they are not circular fringes anymore. Circular fringes, they were like pure circle, but they are hyperbolic in shape. So they are inclined. They are a bit curvy at the edges. You can see here also that they are a bit curvy. Okay, so because of this, we say that this is the hyperbolic fringes. That's where it gets the name. The shape of the fringes determines the name. Okay, so let's go for next one. Okay, so if we have a linear fringes. So if theta is not equal to 0 and both mirrors are also not separable from each other, then we will get linear fringes. So we will get the following representation of fringes after experiment. So we have this M1 and mirror M2 dash. So after the experiment, you can hope to see these type of fringes. Like they are linear. What we will observe is that they will be straight lines. There will be no curves around them like that we saw in the circular and hyperbolic fringes. So because of this unique characteristic of it, we say that these are linear fringes. Okay, so thank you guys. If you have any questions, please tell us about them. Thank you.